Concurrency is easy, said no one ever. It's really quite simple to make mistakes that crash your app and or mangle your data. Needless to say, one of the big features at this year's WWDC was a host of concurrency features with async await taking center stage. Before you learn how to use async await, it's important for you to understand the reasoning behind the language feature. iOS already has a bevy of concurrency features, so adding another one is a pretty big deal. Before I dive into async await, let's take a look at the other concurrency options. The first option is the thread class. The thread class, which is a wrapper around the POSIX thread, otherwise known as pthreads, that comes with Unix-based systems. The thread object allows you to define a path of concurrent execution, but also you have to manage the thread's lifecycle. Being that threads are expensive to create and destroy, a good strategy is to create a thread pool so that you can recycle them. You also need to manage locks when accessing an object state so other threads won't alter it in what are known as race conditions. Mismanage your locking code and you may enter a deadlock situation, whereby two threads perpetually wait for each other to release a shared resource, thereby freezing your program. Needless to say, working with raw threads takes a lot of work that is prone to error. Apple corrected this approach by introducing Grand Central Dispatch, otherwise known as GCD. GCD manages the threads for you. Here you create queues and put blocks of code in your queues for processing. Being GCD controls all the threads, you can focus on your application logic instead. Mind you, while working with GCD simplifies concurrent programming, you can still run into race conditions, deadlocks, and other challenging issues related to concurrent programming, but it's much easier than working directly with threads. Along with GCD, we have operation queues. Operation queues are built on top of GCD, making it easier to use from your application. These days, most developers work directly with GCD, but Operation Queues provide a higher level of abstraction, whereas GCD uses a C like API. Operation Queues also provide some additional features that would take a bit of code to develop in GCD, like priority sorting or a max concurrent operation count. Finally, iOS offers the combined framework, which is a way to asynchronously evaluate values over time. While this year's WWDC didn't provide any adjustments to the framework, it still very much has a place in iOS. In fact, Jesse, my fellow video instructor here at raywinderlich.com, will be producing a video just on this topic, so stay tuned. As you can see, iOS is pretty full with concurrency options. So why did Apple add another one? The truth is, iOS's concurrency landscape produces some bad practices. They lead to what is known as the pyramid of doom, where callbacks are wrapped in callbacks wrapped in callbacks. Error handling isn't clear or concise. You can't just throw an error. Errors are instead passed around between callbacks, confusing the order of execution. Then comes the problem of not even knowing about your current thread context. Apple tries to help with its static analyzer, but it's really easy to become confused. Mind you, these aren't just my thoughts. These issues were documented by Chris Latner, the creator of the Swift programming language. He wrote it in his Swift Concurrency Manifesto that seeks to address the current pain points of writing Swift concurrent code. If you have a chance, definitely check out Latner's manifesto. It's the one manifesto that won't put you on any do not fly lists. Latner details Swift's concurrency problems and puts together a number of solutions, with the first edition being async await. Async await is a language feature that was introduced in C Sharp in 2012 and has since been adopted by a variety of other languages. This is because it makes reading concurrent code easy to understand. Async await doesn't solve the hard problems of concurrent programming, but it does make our concurrent code both clear and concise, which is a huge first step. It allows us to order our concurrent code so we view it just like our synchronous code. Here's how it works. Your program runs line by line. When it reaches the keyword await, that indicates a section of concurrent code. The concurrent code is launched and the calling function may be suspended until the concurrent code is completed. When completed, the code resumes on the normal code path. Now, asynchronous code is marked with the async keyword. By marking a method or property as async, you indicate that the method or property is concurrent. Mind you, if you make a property concurrent, you cannot have a setter. It's a get only property. Async await makes it clear when you are working with asynchronous code, and you also get compile time checking. Better still, our new asynchronous code can throw errors, greatly simplifying our code flow. So, as you can see, async await doesn't replace any of the concurrent options I mentioned earlier. Rather, it makes them easier to use while also providing clarity to your code. Let's see it in action. Here I have Xcode 13 open with the new SwiftUI app. This app will fetch raw JSON from iTunes, convert the JSON into objects, and print them out in a list. You'll see in the model group, this contains an array of music items. This should give me a list of songs produced by a musician. In my case, I'm searching for songs by Leonard Cohen. This can take time depending on network conditions, so this is an excellent use case for concurrency. I start out by opening up contentview.swift. I create a property for an array of songs. Next, I define a simple list to print out the song name and the artist name. Now to fetch the JSON. First, I define a new enumeration for any errors. One is for an HTTP status code, the other is for a failed HTTP URL response conversion. At this point, I want to create a method to fetch the songs. I define a method called fetchSongs, passing in the artist's name. Errors can occur, so I'll mark it as throws. This is going to contain an asynchronous operation, so I need to mark the function as async. This new keyword goes before the throws keyword. Now to write the actual concurrent code. First, I get a URL for the JSON. Now I will make my first asynchronous call. I'm going to make a URL session call to get the JSON. With iOS 15, URL session has been updated to work with async await. This can throw an error, so I need to call try. After the try comes await. This indicates that the function may be suspended while waiting for the concurrent operation to be completed. Now, I'm getting an error letting me know that I can only use the features on iOS 15 or newer. I'm guessing this is an error itself since this project targets iOS 15. To resolve this, I click the error and add an available attribute to the struct. I do the same for the preview struct. Next, I unpack the return tuple from URL session. And now my network request is good to go. The solution is quite concise. Before, you'd have to create a task, write the completion handler, then resume the task after I defined it. Now I simply get the data in response from the URL session. Also notice when I delete the await keyword, I get a compile error because I'm trying to access concurrent code without waiting for it. With this compile time check, I'm made aware that I'm using a method that performs a concurrent operation versus just calling a method and not knowing whether it is synchronous or not. Okay, now I get the response, then I check the status code, throwing errors when necessary. Next, I decode the JSON and update the results. With my function ready, it's time to call it. First, I create a button to fetch the songs. I'm getting an error. Whenever you call an async function, that parent function must also be marked as async. You could mark every parent section as async, but eventually you'll reach your main top level function. Instead, you designate a place in your calling function with the async function call. This allows you to run asynchronous code. It also does some other things which I'll explain in a moment. For now, I build and run. I tap the fetch button, and look at that, I get a bunch of songs. I mentioned that the async function does more than just allow you to call asynchronous code. It also creates a task. A task represents a unit of asynchronous work. It's the context of all your background running code. The async function returns a task handle. This handle allows you to access the context of your background code to check the status of it or even cancel it. Right now, I'm not doing anything with the task handle, but I can capture it. Here, I create a state variable to capture the task handle. A task handle can return a type and whether it throws an error or not. In my case, I'm just updating a property, so I set the return type to void. I'm also handling the error, so I set the error as never. Now I can capture the task handle. Mind you, the task is working at the default priority. You can also specify other priorities like you would with queues. For now, I'll just use the default priority. Now that I have the task, I will allow the user to cancel it. Mind you, canceling a task won't stop the background processing. It will only mark the task as canceled as well as any child tasks. It's up to you to stop the work you are doing. To demonstrate task cancellation, I'll simulate a long running task, such as from a slow internet connection. To do this, I first reset the simulator to clear out any network caches. Next, I activate my network link conditioner, setting it to the edge profile. A network link conditioner allows you to simulate a slow network. This network conditioner is free and available from Apple's Developer Center. The edge profile drastically slows down my connection, giving me time to cancel the task. Next, I check to see if a task has been canceled. I'm using the static is canceled property, which checks the current task context. You can also use the static method task check cancellation as well. Next, I create a button to cancel the task. This requires me to update my UI by adding an H stack to hold two buttons. In my new button, I simply call the cancel method on the task handle. I build and run. I fetch the songs, I cancel the task. You'll notice the cancellation message in the console. Once done, I turn off my network link conditioner. Right now, I'm fetching results based on a button tap. Instead, I want the results to appear on startup. I could use the onAppear modifier, but with the latest version of SwiftUI, we now have access to the task modifier. In this case, I'll fetch my songs using the task modifier. Here, I add my task modifier to the list and call my fetch songs method. The task modifier will run my concurrent code and it will cancel the task once the view disappears. Now I build and run. I see my songs right at startup. This code is great for one song, but what if I want to fetch lots of songs from different artists? I want all the individual tasks to run concurrently. Right now, when I await a task, the function will resume once the task is completed. So if I fetch songs for 5 artists, each task will run sequentially. Instead, I want all the tasks to run at once and resume when all the tasks are complete. To do this, I update my fetch songs method to return an array of music items. I also put in some print statements to show the order of execution. Now I return to my task modifier. I'm going to create a task group that allows a group of tasks to create a result. I can create either a throwing task group or a regular task group. Since my group can throw an error, I'll create a throwing group. I also designate the return type as an array of music items. This passes in a task group. Next, I call my fetch songs in each async block, and it works just like before. When these tasks have